So this is a problem that we did in class earlier. I'm going to go over it again. I know we ran out of time. So it says, let f of x equal x cubed minus 2. And we're trying to find the derivative of the inverse of f of x at x equals 6. So you want to do two things first. First thing you want to do is to check to see if the point, that's x equals 6, is in the range of f. Okay, so we talked about how the range of f is the domain of f inverse. So we want to make sure that f inverse is continuous at 6. That means that 6 has to be in the range of f. The second thing you want to do is, if it's hard to find f inverse explicitly, that's when we use this formula. So if you can just find f inverse, you can go ahead and find f inverse, take the derivative, plug in 6. But if you can't do that, then we can use this theorem. And the theorem says, if f has an interval I as its domain, and f prime of x exists and is never 0 on I, then this. So we'll get to this for a minute. I want to talk more about this if clause. So f has to have an interval I that you can name as its domain. And f prime has to exist and be never 0 on that domain. So we can look here and say that f of x, so we can say f prime of x equals 3x squared, right? So we know that this equals 0 when x equals 0. So we know that 0 can't be a part of our I. So for this scenario, we're going to define I. I also has to include our x point, right? Obviously. It has to include our x point, or else then this doesn't work. So we have to have an I around our x, where this is never 0. So we can define I, right? So we can define I to be 1 to infinity, for example. And that way, the derivative, f prime of x, is never 0 on that I, and our x is in that I. So we have defined our I. And f prime of x exists and is never 0 on I. So now, we're given these two formulas. They're the same thing, just written in with different notation. So I like this one, and this one makes a little bit more sense to me. So we're saying that the derivative of f inverse, which is what we're trying to find, at x equals b, so at some point b, is equal to 1 over the derivative of f, so just the regular derivative of f, which we can find, and we know that it's 3x squared, at x equals the f inverse of b. Okay? So I'm going to go ahead and erase this. Okay, so I'm going to rewrite this up here. So that equals 1 over df over dx of x equals the f inverse of b. So, what is the f inverse of b? That's the next step. So at this point, we're trying to find f inverse of 6. 6 is b, point. So, let's say f inverse of x equals 6. So we're trying to find x. So we can take the function of both sides and say f of f inverse of 6 equals f of x. F of f inverse cancels out, so we get 6 equals f of x. So what is x? Well, what can we plug in for x to get 6 over here? 2. 2 cubed minus 2 is 6. So we can say that x equals 2. And this makes sense because if f of 2 equals 6, then f inverse of 6 must equal 2. So we know that this is the value that we're plugging into our formula for x. So we have this equals 1 over the derivative at x approaches 2, x equals 2, and the derivative of it we found was 3x squared, so that becomes 1 over 12. 3 times 2 squared, 3 times 4 is 12. And so this is our answer. Okay, so we're going to try another problem. I recommend pausing the video and trying to solve this out on your own, and then coming and seeing if you did it right. So let's go ahead and start. So first thing we're going to do is we're going to check to make sure we can use our theorem, because I don't want to find the inverse of this function. So our first check is that our point, which is x equals negative 1, is in the range of f. This is very important. If negative 1 is not in your range of f, then you cannot use this theorem. So please check this every time and make sure that your point is in fact in the range of f. So we're going to say that f of x has to equal negative 1 at some point. Okay, now you can go ahead and solve this and see, but it's a little bit difficult to factor and I don't want to go ahead, it's difficult to solve. But luckily for us, we're told here that f of 3 equals negative 1. Okay? So we know that f of 3 equals negative 1. So we know that for a value of x happens to be 3, our f produces 1. So negative 1 is in the range of f. So that checks our first check that we need to do for our theorem. The second one is that there is an interval I for which the derivative of the function exists and is never 0. So I'm going to go ahead and find the derivative. So f prime of x equals 3x squared minus 6x. And I'm going to try and find where this equals 0. So I'm going to set it equal to 0. And we're going to find that at 0 and 2, when x is 0 and 2, f prime of x equals 0. So we have to define some interval I for which the function exists and for which the derivative exists and is never equal to 0. This interval I also has to include our point B. Okay? So we can go ahead and say that I is equal to, let's say, negative infinity to 0, non-inclusive, right? Because if x equals 0, then our derivative is equal to 0. So this checks, and we know that we can, in fact, use our theorem. So our theorem says that the derivative of the inverse at some point x equals b is equal to 1 over the derivative at x equals the f inverse of b. So we know that b equals negative 1. Now what does f inverse of b equal? Well, we know that b equals negative 1, and we know that f of 3 equals negative 1. So if f of 3 equals negative 1, then we can say that f inverse of negative 1 equals 3. So f inverse of our b equals f inverse of negative 1, which equals 3. So now, we're going to go ahead and say 1 over df over dt as x equals 3. That equals 1 over Our derivative is here. 3 times 3 squared minus 6 times 3, which happens to equal 1 over 9. Alright, so here's another problem we're going to try and do. So suppose the differentiable function y equals f of x has an inverse and the graph of f passes through the point 2, 4 and has a slope of 1/3 at that point. So we need to find the derivative of the inverse of x at x equals 4 at that point. So we're going to go through our two checks like we always do. So our first check is that the point x equals 4 is in the range of our function. Well, we don't know much about our function except for that it goes through this point. Well, what does that mean really? That really just means that f of 2 equals 4, right? So when x equals 2, y equals 4. Well, this automatically tells us that the point 4 is in the range of our function. So check. Now we're going to try and see if we can come up with a range where the derivative exists and is not equal to 0. So we're told that it's a differentiable function, so we know that the derivative exists. And we know that at this point, at this particular point, when x is around 2, our slope is 1/3. Okay? So we can say that I is a range that's very close to 2 because we're not sure what happens around it. So we can say in the range of something less than 2 and something greater than 2. All our I interval does is make sure that the differentiable function isn't 0 basically at our point, because that's when this function doesn't work. So we can check that off because we know that the slope is 1/3 at this point. So we're going to go straight to our formula. We know that we can use this. We can use this this theorem. So we have 1 over df dt at x equals the f inverse of 4. Well, what's the inverse of 4? Well, we know that f of 2 equals 4, so f inverse of 4 must equal 2. So this equals 2. We get 1 over df dt as x approaches 2, which equals 1 over, what's our derivative at 2? Well, our derivative at 2, we know that at the point 2, when x equals 2, our m is 1/3. So that gives us 1 over 1/3, which equals 3.